The Cauchy integral formula gives us a new way to integrate integrals that we've never been able to compute before. So here's a particularly beautiful example of this new technique. Okay, let's say I want to integrate this integral. So it's a definite integral, although improper. It makes no reference to complex numbers, but we are able to compute using complex techniques. So let's see how we might do something like this. The trick is to look at a different integral. Here, I just changed the integrand a little bit. The denominator is similar. So instead of 1 plus x squared, I'm going to write 1 plus z squared, z being a complex variable. And instead of cosine, I'm going to replace that with e to the iz. This is going to be okay in the end because the real part of e to the iz is cosine of z. So we're going to do the integral and then take the real part at the end. We also need to make the path integral be a loop. So we could use the Cauchy integral formula. So instead of going from negative infinity to infinity, we're going to make this loop from negative r to r, and we're going to take a semicircular path back to negative r. So this curvy portion, or the semicircle, I'm going to call gamma. So we're looking at the integral of the semicircular part, gamma plus the real integral from negative r to r. And we're going to evaluate the new integrand instead. All right. So I'm going to rewrite the denominator a bit. So instead of writing 1 over 1 plus z squared, I'm going to factor it. So z squared plus 1 or x squared plus 1 usually doesn't factor with real numbers, but with complex numbers you can. This is difference of squares, z squared minus I squared, right? So you could factor it out into z plus I and z minus I. We could use partial fractions to make this fractions a little simpler and separated. If you do the standard computation, these are the coefficients of a and b that we get. So we can rewrite the integrand as e to the iz times these two fractions added together. Now, these two fractions blow up at different places. So this fraction get denominator equal to 0 when z is equal to negative I. So somewhere around there in the picture. And the second fraction, you get division by 0 when z is equal to positive I. So that's somewhere there. So note that the first fraction, or the first integral, we're going to get 0 because there's no division by 0 inside of the loop. So you could shrink the loop, and then we get the integral equal to 0. The second integral, we could use the Cauchy integral formula. So we basically plug in z equals to I into the integrand e to the iz times 1 over 2I. Okay, so the integral, Cauchy integral formula, we get 2 pi I times e to the I times I is e to the negative 1. And we also have that coefficient 1 over 2I there. The 2 and I cancels out, and we just have pi divided by e. Okay, so we've computed the loop, but we have this extra portion, integration of the semicircle, that we want to get rid of. So what are we going to do is we're going to show that the semicircle portion actually goes to 0 as r gets bigger and bigger, using the ML estimate. So let's see how this works. Okay, so we want to show that this gets smaller and smaller as r gets larger. Let's look at how big the numerator can get. So we're looking at the modulus of e to the iz. And I'm going to rewrite z as x plus iy. If we multiply through the I, we get negative y plus ix. Now remember, the modulus of exponential function is determined by the real part of the exponent. And because we are in the upper half plane, when we go through the semicircle, the imaginary part, or the y, is always positive, which means e to the negative y, the largest it ever gets is when the imaginary part is 0, which happens at the beginning and the end of the semicircle. So that at that portion, the numerator is e to the 0 or equal to 1. Right? So that's the largest the numerator can get. And we could also look at how small the denominator can get, because the smaller denominator means bigger overall. So we're looking at the expression 1 plus z squared. And the modulus of z is r the entire time, because it's fixed on the circle of radius r. So the modulus of z squared is r squared, and modulus of 1 is 1. So we could use the reverse triangle inequality to show that the denominator is always at least r squared minus 1. Okay. And also, to use the ML estimate, I need to know the length of the path. So semicircle, the circumference, or half of the circumference, is going to be pi times r. Using the ML estimate, we can show that the integral cannot be bigger than pi r over r squared minus 1. The power of the r in the denominator is bigger. So as r gets bigger, this does approach 0, as claimed. Okay, so we take the limit as r goes to infinity. We get this complex integral is equal to pi over e, right? Because the whole thing was pi over e, and then the semicircle portion kind of disappears as r gets bigger. All right, now we just take the real part of both sides. So the right-hand side is already a real value, so the right-hand side doesn't change. The left-hand side does change. So e to the iz, if you take the real part, just becomes cosine of z. The denominator is always real, because as z changes from negative infinity to infinity, you are staying on the real line. Okay, then maybe I'll just rewrite the integral. Instead of z, I'm going to use x, because in this expression, you're always using the real value of z, right? Because z is changing from negative infinity to infinity, sticking to the real line. And that's how we computed this integral. I thought this example was very, very cool. And you cannot evaluate it by finding the antiderivative of cosine of x over 1 plus x squared. That doesn't exist. So that's it. I'll end this video here.